Thank you for the kind introduction. So today, as the title says, I'll talk about, let me take this off first. I'll talk about our work towards heat buff algorithmic cooling of a molecular qubit system, which will actually be mostly about characterizing a system that may be suitable for that. So to begin with, a molecular qubit system or a molecular quantum computer is basically a system where the computer is a molecule and its qubits are its nuclear or electron spins. Such systems were used in the past to demonstrate all kinds of quantum algorithms, such as the system in this example. And normally you would need an ensemble of them to get a readable measurement at the end, but these systems suffer from a huge problem, and that is they're really not simple to initialize. Initially, you would get the spins in a thermal equilibrium state, in a highly mixed state, and there's no general easy way to initialize them to a pure state. But heat buff algorithmic cooling is a method that may be used to allow that, to initialize the system. It's a method developed a while back, amongst other by Tal Moore and his group from the computer department in the Technion. I intended initially to give a relatively thorough explanation of what it is, but for the sake of time, I'll give a very hand-wavy explanation. So I'll talk here about polarization, which is just a name used in the ESR and NMR fields to describe the population difference between the two-level systems. So if we have a system with a subsystem, a part that we call the target qubit, that it has a smaller polarization than another part of the system, let's call it the reset qubit. So in other words, a part that is hotter than the other part of the molecule, we can use unitary operations and swap those polarizations to cool the target qubit on the expense of the reset qubit. And then also the reset qubit, we make sure it's coupled to a heat buff, so it can relax back to the heat buff polarization and cool back to its original temperature. And we can continue this cycle a few times to cool even further the target qubit and receive higher polarization even than the original heat buff polarization. And we can use additional qubits we call computation qubits, which are some sort of ancilla qubits to help in cooling the target qubit even further. The takeout message from here is that the requirements we need to be fulfilled in order for this to even be feasible is, of course, first that the heat buff polarization will be higher, ideally much higher than the target qubit polarization, and that the relaxation time for the reset qubit to return back to its equilibrium will be much faster than the relaxation time T1 of the target qubit. Okay, so this heat buff algorithmic cooling was demonstrated in the past, but only by using nuclear spins to cool other nuclear spins, and the gain in these systems is not too high. You have a heat buff polarization which is approximately just 4 times the polarization of the qubit you're trying to cool. However, you may, we want to basically use an electron spin to as our heat buff, and then we'll have a high gain. Our heat buff polarization will be approximately almost 3,000 times the polarization of the qubit we're trying to cool. So the system we're looking at here is a system that was suggested in the past as a good candidate to do exactly that. It's a crystal of malonic acid, irradiated malonic acid. So it's this molecule, which due to the radiation damage, some of the molecules have a free electron here. So that's our electron qubit. And it's coupled to its nearest proton and also to the other protons on the molecule. And depending on the labeling of the molecule, we can also have carbon nuclear spins. If these are carbon 13s, we have additional nuclear spins here. We're using a homemade system with capabilities to both manipulate and read out the state of the electron spin, and also capabilities to manipulate but not read out the state of the nuclear spins. So anyway, I won't get into the full details, but we choose our experimental conditions. And then by using, we start with the simpler type of the molecule with non-labeled carbons. So we basically have only this electron and coupled strongly to this proton, to the nearby hydrogen. And we use a combination of microwave and RF pulses to be able to probe the state of the nuclei through the electron spin signal. So for example, we do this sequence and without RFs, and we measure the echo signal of the electron spin. But when we repeat that with RFs, and if we hit nuclear resonance, then we see a clear contrast between the two measurements, and we clearly see the resonance of the nuclei. I will not get into details, but we can do other measurements in the same manner, such as nuclear Rabi oscillations. We can probe the shape of the envelope of the nuclear echo, for example. And in our system, we can perform relatively broadband scans of the nuclear spectrum. Here we see, for example, the resonance from the nearby proton and the two resonances from the next nearest proton. But what we're interested in here, as I said in the beginning, is to measure the relaxation times of those nuclei. So these are measurements at various temperatures of the relaxation time of the electron spin. We compare that to the relaxation time of the nuclear spin, and unfortunately, they're more or less the same. So this proton is in fact not as a good candidate to be used in heat buff algorithmic cooling. However, we also measure the relaxation times for the next nearest proton, and here the blue graph on the top shows the relaxation times of the nuclear spins and at various temperatures, and the red one or orange one of the electron spin. And we see that here at most temperatures there's an order of magnitude difference, so we can use at least that proton for heat buff algorithmic cooling. Next, we're interested to check, why doesn't it go? Oh. What's the relaxation time of carbon-13 that's positioned close to the electron? Again, we choose our experimental conditions, and here the nuclear resonance, the spectrum is much richer and more difficult to characterize, but thankfully it's easy to distinguish between a carbon resonance and a hydrogen resonance by looking at the Rabi oscillations, because the carbon basically, the Rabi oscillation of hydrogen are faster. So again, we measure T1 of the carbon, and and again, in the experimental conditions we looked at, we get a larger T1, which is good, but not by an order of magnitude. We get approximately 3 milliseconds compared to 0.6 milliseconds. It still means this carbon may be useful for heat buff algorithmic cooling, but ideally we'd want to have a larger difference. So to summarize, I showed a very simple characterization we did. Of course, this is an ongoing work, but characterization we did for the candidate system for heat buff algorithmic cooling. In the future, we hope to work with a differently labeled molecule with the carbon-13s a bit further away from the electron, which is expected to give us better T1, and therefore a system where hopefully we could actually demonstrate heat buff algorithmic cooling with electron spins. That's it. I want to acknowledge people in the MR Lab group and for various contributions, and thank you for listening. That's it.
Question? Yes, sir.
How about your T2 and your gate times? What gets you perform?
So actually, for this part of the algorithm, for the initialization, it's not important. It's all the operations we do are basically either swaps. I mean, we start with our system in the well, a mixed state, but they're on the z-axis, and we only do in a certain way, pi flips and things like that. So we don't create any coherence in the process. That's what I'm saying. But specifically for this molecule, I think, well, it depends on temperature. At room temperature, you'd get an order of 10 microseconds T2, if I remember correctly, but
But did your algorithm improve the T2 or
Hmm?
did your algorithm improve?
No, it's not about improving T2 or anything. It's about actually initializing the system to a pure, or at least less mixed state, to a purer state. Yeah. Yes.
Two quick questions. One, whether these results depend strongly if you work with solids and liquids. And the second question is, can you explain maybe what is the reason in those cases where you see big difference between the electron and the nuclear? What is your physical reason for this difference?
Yeah. So for the first question, in NMR, it's more there are differences if you work with liquid state or solid state, mainly because in liquid state the lines tend to be narrower, so it's easier to be more selective with on specific nuclear transitions. But we with ESR we work in a solid state. In ESR, you don't gain anything from working in liquid state, so it's easier. It's easier to work with a single crystal. In liquid state, you may suffer from. I'm talking about other system. Malonic acid, even with a little bit of humidity, it just melts. So. You can't. You have to work in it in solid state. For the other question, so what affects T1 is basically the overlap, as far as we understand, the overlap of the electron wave function with the nearby nuclei. We're talking about nuclei. It's not the electron and the nuclei it sits around, which in this case you may have p-like orbitals where you have no contact term and everything is great. The closer the nuclei are to the electron, the shorter the T1 is. That's what I hope that answers your question.
Anyone else? Okay, well, thank the speaker again.
Okay.